stage is yours.
Yeah, thank you very much. And first of all, I would like to thank Seba, Antonio, and all the local members in the SOC and LLC for your very hard work on this excellent conference. Okay, so I will present our mid-infrared imaging simulation for FU Ori-type object using E-ELT METIS, which will hopefully start yielding exciting era for our research field in 5 years. Okay. And our institute in Taiwan is contributing to hardware instrumentation, and I'm doing this work for a potential GTO program. Okay. And some of you participated in my preliminary, so my talk about the preliminary results 2 years ago at the conference in Leicester. But anyways, the talk should be new to most of the audience in this room. Okay, so those figures appear several times during this conference, and as we know, near-infrared images towards FU Ori-type object exhibit very beautiful and complicated features, okay, like those. Okay, and I'm extracting those figures from different papers from different first authors in this room. Okay. And okay, so I should remind you, V57 Cygnus is here, over there, but unfortunately this is peculiar even in this peculiar group. Okay, and okay, then so I will skip the details for this target. But regarding regarding the other object, many other features look similar to what we expect for gravitational unstable disks and relative activities. Okay. Edward, Robin, and collaborators used to work hard for those kind of simulations, dynamical and radiative transfer simulations to explain the observed features. If this is the case, okay, one would speculate that gravitational fragmentation induces a FUor outburst and also formation of some very low mass companions like planets and dwarfs. Okay, so otherwise, so some colleagues argue, so these might be associated with enfolding envelope. And in this case, the observed feature would give a useful hint to understand so how the star-plus disk systems are fed, like via streamer accretion. And we've actually seen many talks regarding those topics, so these are definitely the hot topics. But to better understand those features, we want to clearly discriminate between those possibilities. Okay, for E-ELT, the E-ELT METIS will have capabilities for mid-infrared coronagraphic imaging, which is potentially powerful for observing deeper into circumstellar environments. So because of its longer wavelengths, and for which we expect smaller dust opacity. Okay. Suppose the near-infrared emission is associated with an envelope with significant structures deeper across the disk surface, like demonstrated in the optical near-infrared observations of the popular AB Ori disk. But on the other hand, if the near-infrared emission is associated with the disk surface, then we would expect very similar images in the mid-infrared too, because the disk must be very optically thick as those wavelengths. Okay, so thanks to the large telescope diameter, we'd expect angular resolutions, so better than existing observations by a factor of up to 2. And those would also be useful to identify the nature of the observed features. But the question is, can METIS really detect those features those emissions in mid-infrared? Okay, so to investigate this, we first developed a semi-analytic method to estimate intensity distributions in the mid-infrared. Okay, suppose extended infrared emission is either due to an optically thick disk or an optically thin envelope. Okay, their emission mechanism should be scattered light due to illumination by the central source, plus thermal dust emission, whose heating mechanism should be radiation from the central source as the radii of our interest. And okay, central source for the radiation, so for short wavelengths, which is in charge for the heating, so it would be either self-luminous accretion disk or a star, so as proposed by different participants in this conference. Okay, And we estimate the emission from the central source to the disk or envelope using the observed flux. And as Lee Hartman pointed out on Wednesday, so for those two cases, we expect different extent of radiation. Okay, so we calculate the intensity distribution using the observed polarized intensities in the H band and observe the spectral energy distributions. And okay, so for those, I picked those two targets because I have H band images observed using HICHO. So we cannot observe the signal targets from E-ELT, but so it would still be good as this target to try to generalize our results. Okay, so using the polarized intensity distribution in the H band, so we can calculate the disk geometry or optical thickness distribution of the envelope. And using those, we can calculate the individual emission components. For the disk, we approximate it, dividing it into the optically thin surface layer and the optically thick disk interior. And then we calculate the emission for single scattering via the disk surface layer, double scattering via the surface layer and the disk interior, and thermal radiation from those two components. Okay, and okay, so in case for optical thin envelopes, so things are so easier, and we can just calculate for single scattering and the thermal emission from a single component. It's simply because of optical thin nature. Okay, for some technical issues, I didn't include any radiation heating at the disk edge. It shouldn't be any problem if the central source for radiation heating is a disk. But it should matter if the central source is a star. So I will get back to this issue at the end of this talk. But on the other hand, in the mid-infrared wavelengths, the illumination source should be the disk anyway, according to some analysis with spectral energy distributions. Okay, so I will get back to the other assumptions and the approximations. So when I get questions after the talk. Okay, and I have to skip the details of the calculations, but in summary, so we found the calculated emission is dominated by a single scattering process for the METIS wavelengths. Okay. And okay, so these both show the intensities for a single scattering case, normalized by a certain case, and left and right ones are for, when the extended emission is associated with the disk and envelope respectively. Okay, and okay. The horizontal axis is the wavelengths, and anyways, in each box, the dotted and solid lines are so when the central source for radiation heating is a disk and a star respectively, and the different colors are for different dust gray models. Okay, in general, we expect brighter radiation at shorter wavelengths. Or when the emission is from a disk rather than an envelope, and if the central radiation heating source is a disk rather than a star. Okay, but we don't know those natures at this moment, so we have to regard those range as uncertainties of the predicted intensities, which is fairly large even at short wavelengths and long, but very large at long wavelengths. Okay, so let me use METIS simulators for chronography for 3 wavelength bands, 3.8, 4.8, and 11.3 micron. Okay, and the METIS will have a few chronographs with different capabilities and advantages. And I will pick the best one in terms of the field of view and the signal to noise for our observations. And we will tentatively apply 30 minutes integration. And the central disk emission in the mid-infrared, which is marginally extended. So we will use those 4 models based on interferometry to date. Okay, infrared interferometry to date. These are conventional accretion disk model, so with a given luminosity, and the Gaussian distribution, so with half maximum of 1 to 4 AU. Okay. And this plot shows their intensity distributions, so as a function of radius, and the blackish curves are for conventional disk models, grayish ones are for Gaussian disk models, and the bluish bar indicates the corresponding diffraction limit. So all distributions are also within the diffraction pattern, but so unfortunately, so due to some recent complexity, so for coronagraphy, so we still see different extent of leakage from the coronagraph masks from the central source. Okay, and okay, so we applied some observing technique which enhances the signal to noise, and we also subtracted the central emission using a stellar PSF. These are the images before and after the subtraction. So, okay, so we can see the so emission structures much better. Okay. Okay, so these are the simulated images for FU Ori, and okay, so the top to bottom panels are for short to long wavelengths, and the left to right panels are for the brightest cases when the emission is associated with the disk and the envelope, and the faintest cases as well. Okay, and for the central source, I placed the conventional accretion disk for this case. Okay. And the FU Ori is associated with an eastern arm-like feature like this, extended emission. And we see this feature in many of those images. Okay. And the detection rates, detection rates seems better at shorter wavelengths, but worse at long wavelengths. So because of the fainter nature of the extended emission, and also a much larger thermal background noise. Okay, so unfortunately, so things are significantly worse for the worst cases, so with the biggest central disk emission. And so we will see more, much larger leakage from the coronagraphic mask. And as a result, we see strong residuals after the PSF subtraction, which hampers the detection of the extended emission for many cases. Thank you. Okay, so I can summarize detectability of the emission using those plots. Okay, the left and right ones are for different targets, and the top to bottom panels are for short to long wavelengths. And okay, so for each object and band, so left and right panels for when the extended emission is associated with disk and envelope, respectively. And the black curves indicate three sigma detection limits. And the color bars, horizontal color lines indicate the peak brightnesses of extended emission. Okay, so we see 12 cases for each object and band. Okay, and so these will be the detectable cases, which is pretty good. I forgot telling that. For each panel, the short to long wavelengths, for each panel, left to right are for the results for the conventional disk and Gaussian disk with three different half-width half maxima. Okay, and the detection rate is pretty good for the if the disk emission is small and for the shortest wavelengths, but it becomes worse towards the bigger disk and longer wavelengths. Okay, so for our simulation, we have to separate it as a binary companion. So for FU Ori, so we know the binary companion, so with a non-relevant brightness, and I've added this companion for those cases, and for the brightest cases, we can still observe the eastern arm without any problem. But for other objects, we will build a problem if the binary companion is overlapped with the extended emission. Okay, in summary, the E-ELT METIS observation will hopefully be useful for better understanding FU Ori-type object in terms of accretion processes and potential planet formation. But unfortunately, the detectability of the extended emission depends on many uncertainties, including the nature of the FU Ori-type objects themselves and their circumstellar environment and binarity. But anyway, we should start observations from the shortest wavelengths in terms of signal to noise. But even before observing them using METIS, so we may be able to execute preliminary observations using existing telescopes. So I mean, to figure out how the emission would be bright in the L band, for example, or how the binary companion is associated with which object. This will definitely help to establish our strategy for observations. Okay, so I'll also be interested in extending more simulations. Including radiative heating at the inner disk edge and the adaptive heating of the gravitational fragments. And I cannot do it alone, so I want expert help. I have Robin and Edward in mind, but anyway, any other experts, so from this room should be welcome. Thank you.
Thank you, Hiro, for this review. Questions about? And there are many questions. The back.
Hi, great talk. I was just curious about what can we already do with existing telescopes, for example, 8-meter class telescopes and JWST NearCam, maybe.
Okay, so let me start from the JWST. So unfortunately, the inner working angle of the JWST is not very good, so I don't think it's very useful. So for the ground-based observations, so it would be good to, we have, the images in the near infrared, published data in the near infrared anyway. So it would be good to do L-band imaging. And actually, so, we are doing some, we are starting some observations, but of course, you can do too, yeah.
Next question, here.
Thanks very much for the talk. I'm interested in the technical limitations. So if we want to spatially resolve the inner 10-ish AU region, that viscous heating might become important. So would it be feasible to just do PDI imaging without using coronagraph? So would it saturate the camera?
Okay, so let me go back to the figure. Okay, in this figure, okay, those black curves indicate the intensity distribution for the conventional accretion disk, so including the viscous heating, and the emission should be well within the diffraction limit of the telescope. So in this case, we cannot really resolve those viscous disks, and they just provide speckle noise that hampers the detection of the extended emission.
I see. Thank you.
Still, we have time for questions. In the meantime, let me ask, how would it work together with the existing mid-infrared interferometer, the METIS? Because that's even larger, and the shortest baseline for METIS is basically this.
Oh, yeah, okay. Oh, very good question. Okay, yeah, so I've been thinking about that. And actually, so if you can resolve those using METIS, fully resolve those using METIS, that's fine. But if you can resolve them only marginally, so we can use different models to fit the results. So for both using the conventional accretion disk model and the Gaussian disk models.
If there are no more questions, in the meantime, let's thank Hiro again. And let's thank all speakers of the morning for the nice talks.